This is problem number 2 from the Chapter 10 problems I posted on Blackboard. The solutions for problem number 1 were done during our last class, so you can look at the video for that if you want to know the solution for problem number 1. In this problem, we have the grade point averages of students at a large university, and they're normally distributed. Independent random samples of 17 sophomores and 13 juniors attending the university yield the following data on grade point averages. That's in the table below. At the 5% significance level, do the data provide sufficient evidence to conclude the mean GPAs of sophomores and juniors at the university differ? So it wants to know if they differ. All right, so if you notice here in the table, they've assigned the sophomores as population number 1 and the juniors as population number 2. So you just have to be careful, when you use that data, pay attention to the subscript. This is a hypothesis test, and we're using the critical value approach, so you're going to need your 6 steps over here that I just kind of put there to remind us. All right, so let me just move this up a little bit. So the summary data in this table is in the last row there. So they give us the sample mean for each set of data, the sample standard deviation, and the sample size. So those are the numbers we're going to need to finish the problem. So first of all, the first thing we need to do is to define the type of hypothesis test we're doing. When you are comparing two means, so you're doing a two-mean hypothesis test, the null hypothesis is always that the mean 1 equals mean 2. The alternative is going to be either greater than, less than, or not equal to. And in this case, we want to know if they differ. So that's a not equals to situation. This will be a two-tailed hypothesis test. So we'll just remind ourselves of that with a little note here. So we're trying to figure out if sophomore GPAs are different than junior GPAs. That's what these numbers we're looking at, GPAs. That's number 1. Number 2, we need to know the significance level, or the alpha. And in this case, we were asked to do this at the 5% significance level. So alpha equals 0.05. Now, step 3, we need to get our test statistic. This will be the hardest part of this particular hypothesis test, just because of the equations. But the equation to get our test statistic is right here. Okay, and in order to do this, we're going to need our pooled sample standard deviation, so we're going to calculate that first over here on the right. So we fill in the numbers for this. We have n1 minus 1, so that's n1 is 17. Okay, so we're going to get 17 minus 1 times the standard deviation for number 1 squared. So the standard deviation is up there, that's 0.52, and that number is going to have to be squared. And then we add to that sample size number 2 is 13 minus 1 times the standard deviation for number 2, which is up here, 0.3. And just the 0.3 gets squared, not the other part of it. That's going to be divided by 17 plus 13 minus 2. And then you divide that whole thing, or not divide, but you take the square root of that whole thing. And that's our pooled sample standard deviation. So I'm going to go ahead and multiply the top part out here, or do the operations here. So when you're doing this, the first part here, like this part right there, the first thing you have to do is the square, because exponents always come first. So you take 0.52 and you square it, and you multiply it by this number here, 17 minus 1, which of course is 16. So 0.52 squared times 16 equals 4.3264. And then 0.3 squared times 12 is 1.08. So those with the two top numbers equal. And this bottom here, 17 plus 13 is going to give you 30, minus 2, that gives you 28. So that's what's going to be in the bottom. And this whole thing is square root. Don't forget your square root. So when we add the top part up, we get 5.4064 divided by 28. And that equals 0.19, oops, little, 0.1931, square root of that. And so the final number we get for SP is 0.4394. And right now I'm going to do everything to 4 digits, okay, until I get to the end, 4 decimal places. So now that we have the pooled sample standard deviation, we can put it into the equation up here, along with the other stuff. So we have the sample mean for population 1, the sample mean for population 2, so we put those in there, so we get 2.84 minus 2.98. Okay, and in the bottom we get 0.4394 because that's the SP. And then underneath the radical here, 1 over 17 plus 1 over 13. Okay. So the top ends up to be a negative number, negative 0.14, not a very big number. And then in the bottom here we get the 0.4394 times. So when you take 1 divided by 17 plus 1 divided by 13, you get 0.13575. Then you have to take the square root of that, and you end up with 0.3684. Okay, just keep those 4 decimal places there for now. Multiply that out, and we have the negative 0.14 on the top still, and we have 0.1619 in the denominator, and then you divide that out, negative 0.865. So at this point we can go to 3 decimals because we're finally to the end of getting the value for the test statistic. So that's our test statistic, pretty small number. That's going to end up to be a dot on our graph, right? That's our test dot. Our test dot. Dot, test, test dot. Now we need to get the critical lines that'll come from our T critical, T cutoff. This is a two-tailed test, so we remind ourselves this is going to come from the kind of test we're doing and the significance level. This is a two-tailed test, so we're going to have 2 cutoff lines. And since it's two-tailed, we have to divide the alpha by 2, so it'll be 0.05 divided by 2. So we're looking for a t value of t of 0.025. Since this is a t value we're looking at, we need to worry about the degree of freedom, which is related to the sample size, of course. And in this case, the degree of freedom, in these type of cases, because you have 2 samples you're picking from, you have to add up your 2 samples sizes, so that'll be 17 plus 13, and you minus 2 now, and that's 28. So you need to go to row 28 in your chart, row 28, the column for the t of 0.25, and you should find that that equals plus or minus a 2.048. So these will be 2 cutoff lines in your graph. So these are lines in the graph that we're going to draw. So now let me scroll up a little bit. So now let's draw our picture here. Let's see, I'm not sure how I'm going to fit it all. I'll probably just interpret on the side here. But let's go ahead and draw a picture for number 5. I guess I'll draw it on the side over here. So this is a picture of T. Not the smoothest picture, but you get the idea. 0's in the middle, right, for Z or T. 0's always in the middle. We have our cutoff lines now at 2.048 on the positive and negative side. So 2.048 and 2.048 on the negative side. We have to mark where the rejection and non-rejection regions are now that we have those cutoff lines in there. We can do that. So you're going to reject below the negative, you're going to reject above the positive, and do not reject in the middle. Okay, now we plot the test variable there, the test statistic, which was right up here, 0.865 negative. So that's probably going to be like, I don't know, about right there. So negative 0.865, that's right there. And that definitely looks like we just put the test statistic in the do not reject zone. So this is a do not reject the null. Do not reject null, which means we do not use alternative because we didn't reject the null. So in this case, when we interpret it, we would say at the 5% significance level. At the 5% significance level. We didn't reject the null, right? So the data does not provide. The data does not provide enough information. The data does not provide enough evidence to reject the null. So if we did not reject the null, then we cannot say the alternative. And the alternative, remember, was that the GPAs were different. So we cannot say that. So we cannot say the GPA of all sophomores, sorry it's so messy, is different than the GPA of all juniors. So their GPAs are not different. That's what we concluded. All right, let's see if we have time. I think we're going to stop here, and I'm going to do the confidence interval in another video.